don't think there's a weekly assignment.
Yeah, when I first created the weekly assignments in 110, and then I copied all those over to 110A, and at that point realized that everything was hidden and there were no due dates when you copied it, so I had to go through each individual one, which is a lot of fun.
Yeah.
All right, so let's start out with a little conservation of momentum. We've done a number of those problems already. So we'll start out with a 5 kilogram box, move to the right at 4 meters per second. Kilogram box, moving to the left at 6 meters per second. Perfectly inelastic collision. What's the final velocity? It's a collision, so if you see a collision problem, you should I would like you to immediately think of conservation of momentum. This is where it's most useful. Perfectly inelastic collision, what does that mean?
There isn't any extra force exerted after they collide?
No.
No.
Perfectly inelastic collision was the first one that we did.
They stick together?
Yes. So there's only going to be one object, which is why when I said final velocity, I didn't differentiate between the two. So how do we go about solving this? This is where you chime in with brilliant answers. Reduce me to tears of joy. I'll give you a moment to look back over your notes for the collision problems.
Multiply the 5 kilograms times the 4 meters per second.
And what does that tell us?
Where's that?
You faded there.
20 meters, no, 20 kg times m over s.
All right, so if you do multiply, that is the first step. But the follow-up question was, what does this tell us? So if I do 5 kilograms times 4 meters per second, I get 20 kilogram meters per second. What is that?
P,
And what does P represent?
the pitch. No,
The word does not begin with a P.
is the total.
The total what?
The total in the system.
Total, no, it wouldn't be well, it depends on what you consider the system. I was thinking of the system as both objects, so it would not be a total since we haven't brought this into it yet. What does P represent?
The momentum before the collision?
Yes, P in general, momentum.
Momentum.
And why? I don't know why, just P. So the momentum, initial momentum of the 5 kilogram mass before the collision. I guess we've done it initial and before the collision. All right, what is the momentum of the 3 kilogram mass before the collision?
18 kilograms. No. Per meter second.
Say that again?
18 kilograms.
Wow, quite you fades. You can't even see a scowl or a smile on my face. The plus of the mask. It's in my eyes are giving something away. There's actually a mistake there. What's the problem? You are close. And yes, 3 times 6 is 18.
A negative.
Since Jennifer made this positive, she is established that way is positive. Therefore, that's negative 6. So it'd be 3 kilograms times negative 6 meters per second, negative 18 kilogram meters per second. So now we can get into what is the total momentum before the collision. You do not need a calculator for this, but you do need to do some math.
2 kilograms.
Yes. Just to have it. So P initial is is 2 kilogram meters per second. What's the total final momentum? In unison. Let's do a countdown on this one. 3, 2, 1. It would have been so impressive. It's okay, I'm giving you permission to reduce me to tears of joy. What's the total momentum after the collision?
Oh, wait for this. This is 2.
Yes. Kilogram meters per second. It is what conservation of momentum means. All right, so that's got to be equal to the final mass times velocity, since I have only one mass after the collision because they're stuck together. What is the mass now?
8 kilograms.
Times the final velocity. So what is the final velocity? The math problem is 2 is equal to 8v. That's the math problem.
6.
You know, divide the 8 on both sides.
Yep. Divide. And so that's 0.25 units.
Meters per second.
Like you mean it.
Meters per second.
There we go. Yep. For those who came in late, hopefully it's the last time I announced this, my wife has COVID, which is why I'm wearing a mask. If you wish to wear a mask for the extra protection, there are masks up here. Well, that went smoothly. You know what this calls for? Another problem. Let's see if we move a little bit faster here. So what I'm going to do is I'm going to take that same 5 kilogram mass, have it cruise along at 4 meters per second to the right. Take that 3 kilogram mass, have it move 6 meters per second to the left. And this time, they're not going to stick. So this is before and after. Afterwards, the 5 kilogram mass, let's just say it's going to the left at 2 meters per second. The 3 kilogram mass has some final velocity, which we need to figure out. Yes, Jennifer?
What did you say was going to the left for the 3 kilograms?
That's 6 meters per second. Same start as we had over there. All right, so how do we start the problem?
Multiply.
What?
5 kilograms times the 4 meters per second.
Okay, and then?
You get the 20 kilograms times meters over second.
Say that again?
20 kilograms times meters over second.
Okay, and then?
Um,
Oh, okay, sorry, I realized what you did just then. All right, so we have P initial, 20. All right, I get tired of writing. I'm going to define 1 Descartes to be 1 kilogram meter per second. Now what?
You do the same thing on the other side.
Okay, and what do we get?
Negative 18 Descartes.
If you want to go that way, yeah. So that's the 3, and this is the 5. Exactly, the start is the same. Now what? Don't make Monica do this. Or Jennifer. What's the next step?
adding them.
Yeah. Okay. Two Descartes. What is the final momentum? Total final momentum.
2.
Yeah. That's what conservation means in physics. Same before as afterwards. Okay, so instead of, we can't just set that equal to mass times velocity, we gotta do something else extra. So now we have to figure out what our total is afterwards. Well, sorry, we know what it is. We have to break it into parts. What is the final momentum of the 5 kilogram mass? My gut tells me is that more people know it than are speaking. Final momentum of the 5 kilogram mass.
Is it the 0.25 meters per second?
Oh, no, not that.
Would it be 10?
Close.
Negative?
Better. Yeah, because it's now going to the left. When we establish that as 20, then that means that we're saying to the right is positive, especially also when that's negative. Going to the left is negative in just the way it's defined. So this is negative 10 Descartes. So I have to figure out what is the final momentum of the 3 kilogram mass. I know the sum is 2. This is negative 10.
That'd be 6.
How'd you get 6?
Because of the 2, the final.
That's the final momentum.
Ah,
Total. How do we get the 2 to begin with?
From the 2
From, sorry, how did we get that 2?
Adding 20 and negative 18.
Okay, so we got the total by adding the individual ones. So final total is 2. We do it the same way. We get it by adding the individuals. I got negative 10 plus what gives me 2?
12.
Yeah. So if my total is 2 and I know this is negative 10, this has to be 12. Which is equal to mass, 3 kilograms, times whatever its final velocity is. So the math problem is 12 is equal to 3v. That's the math problem.
So it'd be 4.
Give me the whole thing.
4v? Or what? No, 4 equals v.
So the final velocity of the 3 kilogram mass is 4.
Meters per second?
Yeah. Questions up to here? The next question is, are these realistic answers? There's one other thing we need to take into account, which we haven't quite gotten to yet. But what I'm going to do is I'm going to come up with a new formula here. 1/2 mv squared. Now at some point you'll know to love and respect it and to know it. But I'm going to do that initially, so we have 1/2 times 5 times 4 squared, which equals 40. And then over there, I've got 1/2 times 3 times 6 squared, which is 54. Add those two numbers together. Now at this point, I would expect you to look at that, and if you've never had physics before, look at that and go, why 1/2 mv squared? What's special about it? We'll get to that. And now I will need help with the calculator probably. Afterwards, I have 1/2 times my total mass, which is 8 times 0.25 squared. 16th, 1/32. Oh, is that 0.25?
0.25.
Obviously, I feel units off. All right, so I started with 94, whatever these things are, and I end up with 1/4 of one. That's actually possible. Now over here, let's do the same thing. So before, I have 1/2 times 5. Oh, well, this starts out in the same problem, so I have 94 of those 1/2 mv squares. Afterwards, I have 1/2 times 5 times 10 squared, which is
250?
And over here, I have 1/2 times 3 times 4 squared. 24. So I have 274 total. So I started out with 94 of these things, and I ended up with 274. I will tell you, not realistic. Questions up to here before we actually get into what on earth this 1/2 mv squared is.
So after we do this, you would want us to double check if that 1/2 times n times v squared?
There are times, yes.
To see if it's, and how would you ask that in the problem? Like
We
if-
need the language of what we're doing next in order to
Okay.
do it properly.
Okay.
Actually, it'd be what kind of collision is it?
Oh,
This is perfectly elastic as defined there, and this would be what I refer to as flubberesque.
flubberous.
Flubberesque. Textbooks generally call it impossible.
Okay.
The flubber reference, I don't know if any of you have seen The Absent-Minded Professor, or I guess Robin Williams did Flubber. Getting blank looks. Okay. I recommend The Absent-Minded Professor. the original Fred McMurray one. Now, in order to do that over there, we need to do another derivation. And I know that's gonna really excite you. But we do need to do some of that, just so you see where it comes from something, as opposed to the textbook basically says, here it is. And I don't want you to see that there is a rhyme and reason to it. So I'm gonna start out with, I have these two things that are colliding, and I'm gonna start out with Newton's. Well, actually, I have a force on object A. And I'm gonna multiply it times the displacement while that force is being applied, times the displacement. If you flash back a couple weeks when you had two objects colliding into each other, the things that they had in common were they applied the same magnitude of force and they had the same displacement. And so that's sort of why I'm bringing in displacement. This dot right here, it is a dot. It is supposed to be a dot. This is known as a dot product. There are two ways of multiplying vectors. One of them is a dot product, represented by a dot. The other one is a cross product. Represented by a cross. Newton's second law. What is force equal to? All right, so we have the mass of A times the acceleration of A, dot delta x. And the formula for acceleration, the chapter 3 version.
Is it change of velocity of the sound?
It is indeed. So this is mass of A times the change in velocity of A divided by time.